So we're going to pick up where we left off with that first video. It says, starting with example 4, and we set each of these equal to 0. Cotangent x equals 0 and cosine squared is equal to 2. We got that far. So we can see on the right hand side no solution is obtained. Cosine x equals plus or minus the square root of 2 because it's outside the range of the cosine function. And because cotangent x has a period of pi, now we're looking over here, the general form of the solution is obtained by adding multiples of pi to x halves. So we're going to start with this and adding multiples of pi. And because cotangent x equals 0 at pi halves, we come up with this solution pi halves plus n pi. You guys try problem number 41 and come back and check your solution. So in 41 we're going to gather all terms on the same side and then see what we can do. And at this point we have subtracted cosine x from both sides. We see that we have a factor of cosine x in both terms, so we factor that out. We have a product cosine x times cosine squared minus 1. We take each of those, setting them equal to 0 on the right hand side. For the second factor we get cosine squared equals 1, and so of course taking the square root of both sides we get cosine x is equal to the square root of 1, which is just 1. We know that happens at 0 and pi. And cosine x for the other factor equals 0. We know that happens at pi halves and 3 pi halves. Cosine has a period of pi, so we're going to add n pi to each of those. Example 5. Now we are on page 368. If you want to follow along in the book, it says find all of the solutions, and our strategy this time is factoring if we have the quadratic type. So in order to check to see if we have a quadratic function, we can see powers 2, 1, and 0 for our 3 terms. If that's the case, we understand that we can either factor or use the quadratic equation to find values. So we're going to factor into our 2 binomials. We know we need factors of 2 and factors of 1 for our first and last. And we can see that 2 sine x plus 1 and sine x minus 1 give us our original trinomial. We're going to set each one of those equal to 0. Solving on the left side, 2 sine x, subtracting 1 from both sides, dividing by 2, we get sine x is equal to negative pi halves. Checking our unit circle or our memory, we know that that happens at 7 pi over 6 and pi over 6. The right side, the second part of our product, sine x equals 1 because we had sine x minus 1 equals 0, and the sine of x is equal to 1 at pi halves. So for this one we've found all 3. It says on the interval from 0 to 2 pi, so we are not explaining that every n pi intervals we get another solution. We're only interested about solutions on the interval 0 to 2 pi. So you guys take a look at 49. 49 should follow this example closely. You're going to be factoring. Come back and check your solution. So problem 49, I'll get back to you, Leah, on that. Problem 49, we're going to use the graphing utility. So this time we can see that we can factor it, but they'd rather that you put this into your graphing calculator and looked for those roots. So we're going to calculate zeros with the calculator. But I just wanted you to see that we can also factor this, which is sometimes faster than typing that into our function editor. So we get 2 factors, 2 sine x plus 1, sine x plus 1, and we're going to set each of those equal to 0, winding up with the 2 equations. Sine x is negative 1/2 or sine x is negative 1. And we can see that those occur at 7 pi over 6, 11 pi over 6, and 3 pi over 2. And so example 6 takes us to rewriting with a single trig function. If you look at example 6, we have two functions. We have sine and cosine. Remembering our Pythagorean identity, sine squared can be written as 1 minus cosine. So we've removed the sine squared, replaced it with 1 minus cosine squared, and now we can see an equation with just cosine. We're going to go ahead and distribute the two to both and simplify. And I want you to see right here, we simplify to negative 2 cosine squared x. We have that leading coefficient, negative 2. We're going to change that in this step. We're going to divide both sides by negative 1, giving us a positive leading coefficient, which allows us to factor a little more easily. So factors of 2 and positive 1 that add up to negative 3, and we can see that that turns out nicely. 2 cosine x times cosine x gives us our first term, and negative cosine x minus 2 gives us our middle term, negative 3 cosine x. So we're going to take each of those factors, setting them equal to 0. We end up here in this first one, we added 1 to both sides and we divided by 2. Good morning. In the second one, we added 1, and that's all we had to do. So we're evaluating what angle has a cosine of 1/2. We know that to be pi over 3 and 5 pi over 3. And it didn't specify on any particular interval. So we know that we're going to add 2n pi to each one of those. Cosine x is equal to 1 when x is 0. The cosine is 1. So we see our 3 solutions at the bottom. I'd like you guys to try problem 51. And it says to use your calculator to approximate solutions. So we're going to go ahead and plug in that original equation, which you'll see here in the window, for sine x squared minus cosine x minus 1. So we can see from problem 51 we have rewritten the original equation. It said 4 sine squared x is equal to 2 cosine x plus 1, and what we've done is gathered terms all on one side. So we ended up with this equation here, inputting into our function editor, and we can see 2 roots for the range of values that we're interested in. We can see 2 roots, one here and one here, and we're going to assess both of those separately. We have 0.8613 and we have negative 0.8613842. So we have 2 roots that we can estimate at 0.86 and negative 0.86. On to example 7. And at the top of page 369 where we find example 7, it says sometimes you need to square each side of the equation to obtain a quadratic function that we can then use the quadratic formula on or factor. So example 7 says we're going to square and convert to a quadratic type. We're starting out with cosine x plus 1 is equal to sine x. We're going to square both sides of this. That's what we've done here and here, taken the original. On the left-hand side, we're going to FOIL that, cosine x squared plus 2 cosine x plus 1, and on the right side, sine squared x. Again, one of our strategies is to get everything in the same trig function. So we're going to take sine squared x and convert that to cosine as 1 minus cosine squared. We're going to collect all terms from here to here, collecting all terms on the left-hand side by subtracting 1 from each side. Notice those guys disappeared, and we're going to add cosine squared x, getting 2 cosine squared x on the left side. And we also have the 2 cosine x. So we're going to factor out our 2 cosine x. They each have 1, 2 cosine x. That one comes out. We have divided both terms by that. What's left is cosine x plus 1. We're going to set each of our factors equal to 0. In the case on the left, 2 cosine x equals 0. Dividing both sides by 2, we just get cosine x is 0. We know that to be true at pi halves and 3 pi halves, 90 and 270. And on the right side, cosine x is equal to -1 because we subtracted a 1 from both sides. We know that to be true at pi radians. So our two solutions. You guys go ahead and try problem number 53. Well, I want to show you two things here. 53 says to use your graphing utility to approximate. So we're going to input this function, subtracting 1, setting it equal to 0, and finding the zeros. But I wanted you to see this. If we rename cosecant as 1 over sine, cotangent as cosine over sine, and 1 as sine over sine, we would have 1 plus cosine x plus sine x all over sine x. We could look at it that way and start to evaluate and mess around with it. But it just wanted you to put this into your calculator and estimate those zeros. So we can see at roughly 1.57 or pi halves, we have a solution. For our equation, cosecant x plus cotangent x equals 1. So example 8, page 370, it says we're going to deal with functions involving multiple angles. Next two examples involve trig functions of multiple angles of the form sine k times u or cosine k times u. To solve equations of these forms, first solve for ku and then divide your result by k. That seems simple. Let's go through the steps. First thing we're going to do is add 1 on both sides. We end up with 2 cosine 3t, there's our value k right there, is equal to 1. We're going to divide by 2. And the cosine of 3 times some angle is 1/2. So the next thing we're going to do on the interval from 0 to 2 pi, you know that 3t, we know that the cosine is 1/2 at pi thirds, and 3t equals 5 pi thirds. 5 pi thirds. What we're saying right now is the cosine of some angle is 1/2 at pi thirds and 5 pi thirds. So you guys, we're given 3t. Our angle, 3 times the angle, is pi over 3. Dividing pi thirds, dividing by 3 means multiplying by 1/3. We see that t, that's an eraser, t equals pi ninths, and t equals 5 pi ninths. These are the specific solutions on the interval 0 to 2 pi, but we talk about general solutions. All of the solutions would be pi ninths plus 2n pi over 3 and 5 pi ninths plus 2n pi over 3, 2/3 pi. Try problem number 65. And we're back. Problem 65. 65 says we're going to find the sine of twice some angle, and it is negative square root of 3 over 2. I want you to first assess this. If you grab your unit circle, the sine of what angle is negative square root of 3 over 2? And negative square root of 3 over 2 occurs at the sine being y. I see a 4 pi over 3, 4 pi over 3, and 5 pi over 3. Yes, 5 pi over 3. So we know that 2x is equal to this. Twice the angle is equal to that. So in dividing both sides by 2, we get 4 pi over 6, and we get 5 pi over 6. Plus n pi for each. If we're talking about the general solutions, we want to add that cycle or period of n pi. If we're talking about the range 0 to 2 pi, then we know we're just talking about the original answers that we came up with.